Welcome protein coders, let's build some coding muscles. Today we're gonna study strongly connected components by using Tarzan'S algorithm. But before that, I want to emphasize that you need to prerequisite few topics such as Kosaraju's algorithm and Tarzan'S algorithm, which we studied while finding bridges in graph and articulate points. In Kosaraju's algorithm, we have studied that we need to perform 3 steps, right? In each step we are performing DFS. So the time complexity will be v plus e, but it's a 3-pass algorithm. While if we use Tarzan'S algorithm, it will be a single pass algorithm. The time complexity will remain the same. Now let's see it in more detail. While performing Tarzan'S, we have two vectors. One of them is discovery time vector. If you remember, it stores the time at which the node is discovered first time. Then we have a low vector. This will remember the lowest discovery time node reachable, which is reachable from that node. Okay, so let's perform the DFS and mark discovery time and low time. So we'll start from node number 0, and at 5 we see, hey, 2 is already visited and it is not the parent. Kind of cycle found, right? If you remember the Tarzan'S process. Now what we will do, we will update the minimum of node number 5. Low of u equals to minimum of low of u comma discovery time of node number 2, which is discovery of v. And then we will trace back, our DFS will return. And after returning, for the rest of the nodes in the cycle, how we going to update the low? Low of u equals to minimum of low of u comma low of v. Okay, same. Now let's update the low. And if you see, when we reach at node number 2, the low of u is equals to the discovery time of u. And if you see, for all the connected components in the cycle, the discovery time of u is greater than or equals to low of v. And they are all strongly connected components. But if we count like this, we will count all the 4 nodes, right? We need to count them as a single component. So what we will do is, we will only check if the discovery time of u equals to the low of v. Then only we will count the component. Similarly, from 2, if we trace back, the 1 will also be a separate strongly connected component, and 0. So we have 3. Now, what if we need to print the SCCs? We will take the help of a stack. You will see it in a minute. So we will perform the DFS and push the nodes into the stack. Now, whenever we find a condition, discovery time of the u is greater than the low of v, then we will pop the nodes from the stack and store them in a vector. Okay, till the discovery time of u equals to low of v. So if you see, when we return in the cycle, we will mark 5, 4, 3 and 2 in a single component, then 1, then 0. Let's perform similar operations in this graph. We will perform our DFS, push the elements into the stack, and also initialize the discovery and the low time while performing the DFS, right? And when we saw a node which is already visited and it's not the parent, we will trace back the DFS, right? And we got our first strongly connected component 6, 8 and 7, right? Then we will pop them from the stack and continue the DFS. But you see, at node 5, we will perform the similar operation, right? And our DFS will return. But when it reaches the node number 3, it will see 6 is also visited, and it has a discovery time lower than the low of 3. So it will update it as 2. Now when I return from 3, I will update the low of 2 also, right? Node number 2. Then at 1, I will stop. Hey, what just happened here? I got 5, 4, 3, 2, 1 as a single connected component, which is wrong, right? The problem is this comparison of the node number 3 with the node number 6, which is already visited. But if you see carefully, 6 is not the part of the stack, because we already popped it out when we found out it was a part of another strongly connected component. So we will take a stack boolean vector in stack, which will remember that this node is in the stack or not. And that's it. So let's articulate what we have studied. We'll perform the DFS, push the elements into the stack and mark them in the stack, right? Initialize the discovery and low time. And when we find some neighboring node is visited, we will check if it is in stack or not. If it is in stack, then only we will update the low. Okay, if it is not, then we will just ignore it. we will update the low, and if the node is not visited, we will simply call the DFS, and while returning we will again update the low. Okay, simple Tarzan'S algorithm. So that's it. And one more thing, at the end, if we want to print the SCCs, what we will do is, when we found a condition where low of u is equals to the discovery time of v, then we will pop the elements from the stack, okay, till we get the stack top is equals to the node. Let's see it in the code, you will understand better. Let's initialize our timer, discovery time vector, low vector, in stack vector, a stack, and a vector of integer to store our SCCs, okay, strongly connected components. So you have to initialize all of them in the main function. So let's write our DFS. First is mark the discovery and the low time and increase the timer, and push the node into the stack and mark that this node is in the stack. So we will mark in stack u of equals to 1. Then we will traverse, and if the discovery time of v is equals to -1, that means it's not visited. We are using this because we don't want to use an extra visited vector. Then we will simply call the DFS and update the low. Or else if it is visited, then we will check if it is in stack, then only we will update the low. Of u equals to minimum of low of u comma discovery of v. Okay, if it is visited and in stack, then only we will update. Now at the end, after the for loop, after checking all the neighbors, what we will do, if we got a condition where low of u equals to discovery time of u, we will take a temporary vector and run a while loop in which we will pop the elements in the stack and push them into the temp till u equals to v. Right, at the end we will push the temp vector into the SCCs or our answer. Right, so let's revise what you have studied. You have studied in Tarzan'S algorithm, it's a single pass algorithm, similar time complexity with Kosaraju. Right, and here we saw the condition for the SCCs, the discovery time of u should be greater than or equals to low of v. But for counting, we will check discovery time of u equals to low of v. Then if you want to print them, we take help of a stack. Right, and we saw how we're going to use the stack. Then we got one more observation, like before updating the low, right, we need to check whether the neighboring node is visited and not parent, but it should also be present in the stack. Right, if it is not in the stack, that means it's already a part of a SCC and we don't need to update the u. Then we saw the code for it, right? We initialize all the vectors and timer integer and stack. Then we initialize the discovery and low time, push the node into the stack, marked it in stack. Then we traversed all its neighbors. If they are not visited, then we will simply call the DFS and update the low. Else, if the neighboring node is visited and in stack, we will update the low. At the end, we will check the condition. If low is equals to discovery of u, we will run a while loop till u is not equals to the st.pop, and we will store all the elements from the stack. So that's all from my side, guys. If you have any queries, please mention them into the comment box. You will find the problem and the solution link into the description box. Hope this helps. Keep smiling, keep practicing. Thank you.